Welcome to this video lesson on polarization. It has spec reference 3.1.3.6. And in this lesson we've got three main questions to answer. First of all, we need to understand what electronegativity is, in particular in connection to bonding. And then we need to look at the difference in electronegativities between two atoms within a bond, and how that creates polar covalent bonds and permanent dipoles. And lastly, we want to understand what partial charges are and how we use those to indicate polar bonds. So first of all, electronegativity. So electronegativity is the greediness of an element for electrons, and when that's related to covalent bonding, we say that electronegativity is the ability of an atom to attract the bonding electrons towards itself in a covalent bond. And we can measure electronegativity quantitatively using a scale called Pauling scale from a chemist called Pauling. So why don't we just write that down so we can remember it a bit more easily. So it's called the Pauling scale. So let's say high electronegativity is at the top and low is at the bottom. Then if we look at fluorine, for example, you're probably aware that fluorine is the most electronegative element in the periodic table, and that has a Pauling's reading of 3.98. The next most electronegative element is oxygen, and that has a reading of about 3.40. Then we have chlorine, which has a Pauling scale of 3.16. And then nitrogen, 3.04. So those four elements are the four really electronegative elements, and after that you get the sort of elements that are neither really electronegative or electropositive. All the metals, of course, would have much more smaller readings, in fact less than 1 for the group 1 metals. But carbon is interesting to list out. Carbon has an electronegativity of 2.55. And hydrogen is also interesting. 2.20 is the Pauling scale reading for hydrogen. And the point of notice, I suppose, is that the difference in electronegativities needs to be about 0.4 before you start getting a noticeable movement of electrons. So now we're going to have a think about non-polar covalent bonds. Non-polar covalent bonds. They're the bonds that you're familiar with already, that are those where the two atoms share the bonding electrons equally. So if you imagine, for example, a hydrogen molecule, where you've got, so hydrogen, as you know, is H2, and that is two hydrogen atoms that are covalently bonded together. And let's draw one of the electrons as a cross. That's the left-hand hydrogen atom, we'll say, and we'll draw the other electron like this. And one hydrogen atom has the same electronegativity as the other hydrogen atom. So these bonding electrons are neither going to be pulled in that direction or that direction. And so this is what you call a non-polar bond, where polar means that it's going to have some sort of difference in charge between the two atoms in a bond. So this is a non-polar bond, and all of the diatomic gases. So you could also write chlorine, for example, which is very similar. You've got two chlorine atoms covalently bonded together, and again our electrons are going to be pulled equally in both directions. All right, so they sit most of the time, they're most probably found right in the middle of the two chlorine atoms. And so that's a non-polar bond, and all diatomic molecules would be like that, because by definition the electronegativities of two identical atoms are going to be the same. It's worth also mentioning a carbon-hydrogen bond. Right, so let's take a methane molecule, for example. So we'll draw the displayed formula of methane, and you'll remember from the previous slide that the electronegativity of hydrogen is 2.2 and the electronegativity of carbon is 2.55. And didn't we say that the difference had to be about 0.4 before it makes much of a noticeable difference? And the difference here is 0.35. So not much of a difference in electronegativity between carbon and hydrogen. So if we represent the carbon bonding electrons with these blue crosses, 4 of them, and if we represent hydrogen's electrons that they contribute to the covalent bonds with our red dots, because the electronegativities are so close, we're not going to get a noticeable polarity in that bond. So these bonding electrons are going to be slightly pulled in towards the carbon, because carbon has a greater electronegativity than hydrogen, but not so much that you'd really notice it. So methane is, and all carbon-hydrogen bonds, unless there's another influence going on altogether, so all carbon-hydrogen bonds are qualified as non-polar bonds. Okay, so another type of covalent bond is a polar covalent bond. So a polar covalent bond, and in this case we're talking about electrical poles, not magnetic poles. And so a polar covalent bond is going to be where there's a difference, where one end of it is going to be positive or slightly positive, and the other end of it is going to be slightly negative. Okay, so we've got a covalent bond here where the electrons, the bonding electrons, are not shared equally. All right? One of the atoms in the bond is going to attract the electrons towards itself, or be greedy for those bonding electrons. And an example of such a molecule would be hydrogen chloride gas. So hydrogen chloride is just one atom of each in the molecule. So there's a covalent bond between the hydrogen and the chlorine. And you'll remember from the start that the electronegativities of the two elements, hydrogen was 2.20 and chlorine was 3.16. So now we've got quite a big difference in electronegativity. That's about 0.94, I think. Okay, so that is going to make a big difference in where these electrons are most likely to be found. So let's draw these electrons on. So let's make the blue cross be the chlorine bonding electron, and let's make the red dot be the hydrogen bonding electron. And you can see these two electrons are no longer in the middle of the bond. They have moved from the middle of the bond towards the chlorine. And what that means, of course, is that this is a negative charge cloud, right? It's been drawn away from the hydrogen atom, leaving it slightly positive. And when we want to say slightly positive, we use a small Greek d, delta positive, so we call that delta positive. And if that negative charge cloud is nearer to the chlorine atom, then that is going to be delta negative. And now you can see we've got a difference in charge, or more normally called a difference in polarity, between the two ends of the bond. We've got one end is slightly positive and the other end is slightly negative. And so we call this a polar bond. And another way of describing a polar bond is to describe it as a dipole. Di being 2, and pole in this case being the electrical charge, the difference in electrical charge. And often these polar bonds can make the whole molecule polar. And in that case that we just looked at with hydrogen chloride, where the chlorine atom was delta negative and the hydrogen atom was delta positive, because the two electrons had been drawn towards the chlorine atom. That was a polar bond, and we can also describe it as a polar molecule, because there is nothing to cancel out that polarity there. And the way that we draw that is we draw it with an arrow cross combination like that, and this points from the positive to the negative end of the molecule, and it indicates a permanent dipole. Indicates a permanent dipole, which is just another way of describing a polar molecule. And all it means is that the polar bond is not cancelled out by anything. So that doesn't always happen. Sometimes you have polar bonds in a molecule that are cancelled out, in which case the whole molecule won't be polar. And I'm going to give you an example of that now, which is carbon dioxide, in fact. So let's draw carbon dioxide. You know that carbon is double bonded to two oxygens, and so what you would find is that oxygen is very electronegative, and so that's going to draw these electrons in the bonds towards itself. So the electrons are going to be drawn in the direction towards the oxygen atoms, which would mean that both oxygen atoms would be delta negative, leaving the carbon atom delta positive. So these two polar bonds cancel each other out. So this is not a polar molecule. There is no permanent dipole. Let's do another example to illustrate this polar molecule concept. So let's have a look at water. So water, we have a molecule that is shaped like so, and oxygen is much more electronegative than hydrogen, so these bonding electrons are going to be drawn towards the oxygen, which is going to make the oxygen delta negative, and each of the hydrogens is going to be delta positive. And these two polar bonds do not cancel each other out because they don't operate in the opposite direction. And so how we would write our arrow is we'd go from the positive side like that towards the negative side like that, and that would be our polar arrow to indicate the permanent dipole. We'll do one more example. Why don't we do difluoromethane? So difluoromethane has a formula of CH2F2, and it's shaped such as this, where we've got two hydrogens in a pyramid shape. So we've got a hydrogen going out of the page, going back into the page like that, and then we're going to have a fluorine coming out of the page, and we're going to have another fluorine in the plane of the page like that. And the difference in electronegativity between carbon and hydrogen is small, and so the carbon-hydrogen bonds are not going to be polar. But the electrons in the carbon-fluorine bonds, they are going to be affected by the difference in electronegativity. Fluorine is much more electronegative than carbon, right? So these bonding electrons can be drawn towards the fluorine, which can give the fluorines a delta negative, and that would leave the carbon atom as delta positive, like that. And indeed, that delta positive might just draw these electrons towards itself a little bit, but it would remain delta positive because fluorine is the dominant force here. And so our permanent dipole arrow would be drawn like this. So we've got the direction that I've drawn there from positive to negative, going from the left to the right in the direction of that arrow. That would indicate our permanent dipole. And that brings us to the end of our little video lesson here on polarization. And I think we discussed electronegativity being the ability of an atom to draw the bonding electrons towards itself in a covalent bond. And we looked at the difference in those electronegativities. When it's greater than 0.4 from the Pauling scale, then you create a polar covalent bond. And when that is not cancelled out by another polar bond operating in the opposite direction, then you get a permanent dipole. So we've done that one. And we also looked at partial charges, whether they be delta positive or delta negative. And we used those to indicate the polar bonds. And we also drew our permanent dipole arrows in the direction of positive to negative, like that. And that's the whole lot. I hope that's been clear.